In this video, let's solve an interesting problem. Here is a problem description. Given a string which contains only lowercase letters, we need to remove duplicate letters so that every letter appears only once. And there's many ways of removing duplicate characters. However, the result have to satisfy the following criteria. It must be the smallest in lexical order among all possible results. For example, for BCABC, we can remove this B, we can remove this B, and we can remove this C, or remove this C. But however, ABC is lexicographical order smallest among all the other possibilities. For example, BAC is larger, ABC is smaller. And what is lexicographical order? The lexicographical order, let's take a look at an example. For example, this string is smaller than this string. The reason is we compare from the leftmost character to the rightmost character. The A is smaller than B, so this string is smaller. The rest of the characters doesn't matter. Okay, this is how the lexicographical order is decided. Let's take a look at another example. This one and this one. This string is smaller because A and A at the first position is the same. At second position, A and A is the same. At the third position, B is smaller than C, so this string is smaller. The rest of the characters doesn't matter. Now we know what is lexicographical order. Let's try to approach the problem. So if we scan the characters from left to right, and during the process we try to remove the as many characters as we can, while still keep the criteria. All the characters are in the string, and they are lexicographically small. How we do that? So let's take a look at this example. We first process B, okay, and then we add a C. BC is fine. If we remove B, the lexical order will be larger because C is larger than BC, so we need a BC. We don't remove anything. Then we process BCA. This string doesn't make sense anymore because if we keep BC, right, the BCA is larger than A. And so we should use A instead of BCA in order to reduce the lexicographical order. And remove B and C is okay because it won't violate the criteria. We need each character in the final string because we have another B and C at later. Adding the B and the C later will have a smaller lexicographical order. So let's remove B and C. We see so far. Let's keep A. Then later we add B and C. So final string is ABC. Final string is ABC. So this is this example. Let's take a look at another example. For this string, first we read in M. Then we read in N, then we read in Z. This is fine because if we remove M, the lexicographical order will increase because N is larger than M. If we remove both M and N, the lexicographical order will increase because Z is larger than the whole string. So at this point it makes sense. But if we add a B, this string doesn't make sense because the whole string is larger than B, we should have removed the first 3 characters and keep B because B is smaller than all those characters. Remove M and N is fine because remove this M and N, we still have chance to add them later, and it's lexicographical is smaller if we add them later. However, remove Z is not okay because this is the last chance we add it to the final string. If we remove Z, it won't be it will violate one of the criteria we see before. Each character have to be in the final string, so it's not okay to remove Z. We have to keep Z. In order, if we have to keep Z, we have to keep M and N as well, because if we only keep Z and remove M and N, the lexicographic order will be larger because Z is larger than M and Z. So we have to keep all those strings. So this unique character Z shows M and N and itself to be removed by later characters. All those characters enter the final string. The problem changed to another one. It changed to what characters in this substring should enter the final string. Those strings already final because of this unique character. Now let's process further. After we have this string, right? It is fine. Then we reading A. This string no longer makes sense because B can be removed in order to decrease the lexicographical order. If we remove B, it's okay because B can be added later. So we remove B, we get M and ZA instead. Then we add M, right? We add M. M should be removed. First of all, this is a duplicate. We should remove it. Keep it will increase the lexical. We cannot remove this M because it's final. We can remove this M. It's duplicate and it's increase lexicographical order. So we end up have this string again. Now we add N. N should be removed as well because this one is larger than this one. So we use this instead. Finally, we add B. And in this case, B is unique. This is the last chance we can add a B. So finally, we have this string, M and Z, A, B. As we observe, when we scan the characters from left to right, only 2 kinds of characters will left in the final string. One is the global minimum character. Any characters comes before this character will increase the lexicographic order, therefore should be removed. And unless a character is unique, so it brings us to the second criteria. The second kind of character will remain in the final string as unique character. Unique character can be removed no matter how big it is. As a result, a unique character shows all characters come before it. And all the characters come before the unique character can no longer be removed by the later characters. So it set a point, all the strings exists before it became final. And the unique character is a character we see as the last position. Okay, so it don't have to be unique. The last time we see it, even a duplicate character became the unique character. With the stack, we can simulate the above process. From left to right of the string, we push the character into the stack. Before a character enters the stack, it need to do the following task. It have to pop out all the characters larger than it until the stack is empty, or it meet a unique character, which will shield all the characters before it. And then the character enters the stack if it is unique. Finally, when we reach the end of the string, whatever left in the stack is the final result. So here is a code. We have the we first go through the whole string. Remember the last chunks, we are able to add the character. And once we reach this position, this is our last chance to add it, and this character, if they are not in the final string, it became unique. And then we scan the characters from the left to the right of the string. For the current character, if we already see them in the stack, there's no reason to add it again because it's duplicate. It will increase the lexicographical order. Only when we have it's not in the stack, then we will try to add it. It first need to clean the stack. How it clean the stack? If the stack is not empty, and the element at the top of the stack is larger than the current character, and that element on the top of the stack is not unique, then we will remove that element. We will pop it out from the stack. So we pop it out from the stack. Once the stack is cleaned, this element entered the stack and waiting to be removed by later characters or get shielded by a unique character. Finally, when we reach the end, we print out everything inside the stack. That is our final result. Okay, the time complexity is O(n) because even though we have two loops, the inner loop won't be bigger than 26 because we don't allow duplicate in the stack. So the stack size at a maximum can be 26, no matter how large the string is. So the time complexity is O(n) instead of O(n) squared. For the same reason, the space complexity is also O(n). Okay, this is this interesting problem. Decide which characters enter the final string.